It says figure 9.1 shows a simple relay used to switch a mains electric motor on and off. So we can see that this is the coil and it is connected to a battery and a switch. So when the current flows through the coil becomes a magnet, and when it magnetizes, it pulls the iron armature towards itself. When the iron armature moves towards the coil, the upper contacts get closed, and when they close, the circuit for the motor is completed and the motor is switched on. And similarly, when we break this circuit and we switch off and open the switch, then there is no current flowing through the circuit. And when there is no current flowing through the circuit, the coil demagnetizes. It does not pull this iron armature anymore. So the contacts again open, and with the open contacts, the motor is switched off. Now the first part says explain why the motor switches on when switch S is closed. We have to describe the mechanism why it switched on when the switch S was closed. So number one, current flows through the coil and the core is magnetized. So when it is magnetized, it attracts the iron armature. When iron armature moves towards the core, the contacts are closed. So this is how the motor is switched on. Again, when the current flows, the iron armature, uh, the coil, and this iron core is magnetized and it attracts the iron armature. When it moves towards the core, then the contacts get closed and the motor is switched on here. Explain why the core is made up of iron rather than steel. We know that steel is a permanent magnet and it is a hard magnetic material. So when we switch on the circuit, it would take time to switch on the motor, and when we close the switch, it would retain its magnetism and the motor would not get switched off quickly. So the motor stays switched on even when the switch S is closed. So that is why steel is not a good choice here. The next part is a student suggests that the motor can be turned on and off without a relay. He suggests connecting the mains to a simple switch in series with the motor. Suggests one reason why in some situations using the relay is better. So a relay is better because the switch is connected to low voltages. And when we connect it directly with the motor, then it is connected to high voltage because the motor would be um, making a large current flow through the circuit. So that would affect the switch also, and it could melt and get short circuited and could be a cause of electrocution as well. Figure 9.2 shows the coil of a wire wrapped around a cardboard tube. There is no core. There is an electric current in the wire in the direction shown by the arrow. So this is the direction of the current in which the current is flowing. Now, on figure 9.2, draw the pattern of the magnetic field inside and around the coil. Mark the direction of this magnetic field also. On figure 9.2, mark the north pole of the coil. We know that the magnetic field of a coil is similar to the magnetic field of a bar magnet, and the north pole of the magnet is found using the right hand grip rule. So when we align the curl of the fingers with the flow of the current, the thumb is pointing to the right. So this one is going to be the north pole over here, and this would be the south pole. Now about making the diagram. I'm making 3 horizontal lines within the coil. So this would be the first line, which is going through the coil. This is the central line or the middle line, and this is the third line. So these lines should be parallel to each other and should remain straight when passing through the coil. Now after this, it would take a turn like this and would make a loop, and then it would return to the south pole. So this is how one loop is being made here. Similar loop could be made using this line. So this would be the direction for this loop, and this line should be continued straight because it is exactly at the center, and the arrows would show the direction of the magnetic field. So if we draw at least 2 loops and 3 lines within the coil, then the direction and the magnetic field, the pattern of the magnetic field is completely explained, and we have also marked the north pole over here. Okay, the supply of current to the coil is removed. The ends of the coil are now connected to a sensitive ammeter as shown in the figure. Now there is no current flowing through the coil, and it is connected with a sensitive ammeter. Describe how a permanent magnet is used to produce a large reading on the ammeter. So we could use a permanent magnet here to produce current through this coil, and this would happen when the cutting of magnetic field lines would take place. That would induce an EMF in the coil, and since the circuit is complete, there is a complete closed loop or path for the current, so the current would start to flow, and when the current flows, there is a reading on this ammeter. So one way of doing it is that move a magnet towards or away from the coil and move it with a larger speed. So when it is moved and moved with a larger speed, a larger reading on the ammeter is produced. Explain why a current is produced. Because coil is cutting the magnetic field lines, and an EMF is induced in the coil. So the current flows in the complete circuit. Circuit is also complete here. So the current is flowing. So this is a basic phenomena. When we take a bar magnet here, we move it towards the coil or away from the coil, the magnetic field lines coming towards the coil would get cut. And when it is cutting the magnetic field lines, EMF is induced. And because of the induction of EMF, current would flow through the coil.